even though I didn't really emphasize it, there are several ways to solve exponential equations. I really emphasized just one. But with logarithmic equations, there's two approaches, and we're going to go through both of them and use both of them. It's just, you kind of need both of them depending on the type of problem. So the first one is this. If the log of A equals the log of B, so you have the log of two things that are equal. If that's true, then A equals B. It looks as if you're canceling out the log on both sides. You're just going, okay, get rid of it. That's not really what's going on. And if you did something like that, I'd be a little bit unhappy. But I can't stop you from thinking that. The bottom line, though, is if you have the log of two things that are equal, then those things are equal, the A and the B. So let's apply that. Now, one thing you need to keep in mind in working with logarithmic equations is the domain of the log. And I regret on the last test I didn't test you on domain and one-to-one functions. So you got to pass on that one. But the domain of the log function, the values of x that you can put into the log function, have to be greater than 0. So domain of the log of x is that x is greater than 0. You cannot take the log of something that's less than 0. Now in this section in particular, we have to be a little bit careful about that. We want to make sure that our answers don't create any kinds of problems. We'll start with problem number 50. The log of 3x plus 5 equals the log of 2x plus 6. This is tailor-made for the first addition. So, the first method here. You have the log of something equals the log of something else. Well, I'll let you leave a space here. What that works out to, though, is that 3x plus 5 equals 2x plus 6. Now, there's really a step here that we don't need to show that's there, but we don't need to show it. Well, I want to solve for x here, so I can subtract 2x from both sides. And I guess it depends on how much of a hurry you're in. If you want, when we subtract 2x from both sides, we can also subtract 5 from both sides. Let's get this all done at once. So what equation's left? X equals 1. And you can check that pretty easily. If you put in a 1 here, 3 times 1 plus 5 is 8. 2 times 1 plus 6 is 8. So you get the log of 8 equals the log of 8. It checks. In fact, checking your answers with logarithmic equations is more than just a good idea. Sometimes it's an absolute requirement. The step that you're missing, the step that makes this true, if you write this on a test, I'd give you extra credit. You're not just canceling the log on both sides. You're actually doing something to both sides to make that happen. You're exponentiating both sides. 10 to the log base 10 of 3x plus 5. 10 to the log base 10 of 2x plus 6. I guess I don't need to write the 10 there. It's understood. But what's happening is that this function and this are inverses of each other. They cancel each other out. So that's really the hidden step there. But you don't need to show that. Okay? You just don't. So if you're less confused this way, if you want to just jump ahead, that's fine. I want you to get this problem right rather than worry about that point of extra credit. Let's try another one like that. Problem number 52. Log of x squared plus 4x equals the log of x squared plus 16. Now this little trick here of getting rid of the logs only works if the bases of the logs are the same. And in this case, They are. You've got base 10 and base 10. Vincent, can you tell me what the next line in this problem is going to look like for us? Perfect. X squared plus 4x equals x squared plus 16. In terms of solving, we could subtract x squared from both sides. You get 4x equals 16. So what does x have to equal? 4. Good. So x equals 4. You can check that. If I put it in here, 4 squared is 16. 4 times 4 is 16. So I get the log of 32. And 4 squared is 16 again. 16 and 16 gives me 32. So I get the log of 32 equals the log of 32. It checks. Let's keep going. Problem number 62. You know what? I think we've done enough of these ones. Let's just jump up to problem 78. Log of 3 minus 2x minus the log of x plus 9 equals 0. Now here's a place that if you just canceled out the logs right now, you probably could stumble upon the right answer, but I'd be pretty unhappy to the point that you might lose a little extra credit here. So I can't. I don't have log of something equals log of something else, but I'm pretty close to getting that though. Does anyone see what I can do to get log of something equals log of something else? All right. Good. Let's move that to the other side. And when it moves to the other side, what changes about this log term? The sign. Good. So this becomes a log of 3 minus 2x equals a log of x plus 9. Please don't cancel. Don't get rid of the logs at this step. It's only at this step that you can really apply that idea and get rid of the logs. The next equation here in this problem would be what? Thank you. 3 minus 2x equals x plus 9. Let's add 2x to both sides. And at the same time, what else can we do? Subtract 9. So I get negative 6 equals 3x. So what do I get for x? Negative 2. Now, do I have to throw out negative 2 because negative 2 is not in the domain of the log function? No. What I said is that you can't take the log of a negative number. Negative numbers can be solutions, though. And if you carefully check it, I get the log of 3 minus 2 times minus 2 is really going to be plus 4. So I get the log of 7 equals a log, I guess I should have checked it in the original equation. I'm checking here. Log of negative 2 plus 7, or negative 2 plus 9. Basically, I get the log of 7 equals the log of 7. It checks. And I'm sorry, I really should have checked this in the original equation. I accidentally wrote the second line, but it'll check in the original equation just as well. So we're kind of transitioning towards the other type of logarithmic equation, or the other method we're going to use to solve logarithmic equations. That was one kind of step where we had to do a little work to set up our log of something equals log of something else. Problem number 72 is yet another equation like that, where we're going to have to do a little bit of work to kind of get going here. Log of 2x minus 5 over 2 times, is it x plus 8? Let me just double check the equation. Is it 2 times x plus 8 in the denominator? Yes? Okay, thanks. 2 times x plus 8 in the denominator. And that's equal to 0. There's really a couple different ways we can solve this. Maybe when we learn the method that follows this, we'll go back and solve it. But let me just distribute that and call it 2x plus 16. But you're right. So the first step is to use your properties of logs, the quotient rule, right? Log of a quotient is the log of the numerator minus the log of the denominator. Okay, cool. What can we do from there? What should we do from there? Grace? Good. Add that to both sides. When I do, that's going to move to the right-hand side and become positive. Uh-oh. I'm seeing a problem. All right. Well, let's keep going. What equation do I get here? Two x minus 5 equals 2x plus 16. If I subtract 2x from both sides, what do I get? Yeah, minus 5 equals 16. Uh-oh. Houston, there's a problem. All right. So what the problem is that there's no solution here. Because negative 5 doesn't equal 16, so there's no solution. The big thing that you should pick up from this problem, though, is this. That we first use the quotient rule, then we move this term to the right-hand side in order to solve. And that helped us, get the log of something equals the log of something else. And from there, we got rid of the logs. So that's the big thing you should get in this problem. Yes, sir? I don't know. Somebody said that I copied that right. I wasn't too sure. Oh, yeah. I did. I did change the problem a little bit. So what do you get when you cross a dyslexic, an atheist, and an insomniac? A person who lies awake late at night pondering the existence of dog. All right. Yeah, all right. I will keep my day job. Thank you, Tracy. All right. All right. So, all right, let's go back and do problem 72 the way it was actually supposed to be done before I was dyslexic this morning. So I did have the denominator right. So do I get partial credit? Log of, what was it, 5 minus 2x? No. It wasn't 5. 2 minus 5x. All right, there we go. 2 minus 5x over, and then I had the denominator right. You know, I hate it when they don't distribute. 2 times x plus 8 equals 0. Let's just distribute that right away. Log of 2 minus 5x over 2x plus 16. I thought that was kind of weird that we got one that didn't work out. I didn't expect that one in this case. So, okay. Well, since we've practiced this one a little bit, why don't you go ahead and see if you can't solve it? Okay, so as before, we'll use the quotient rule. Then we'll move this to the right-hand side. I get log of 2 minus 5x equals a log of 2x plus 16. Please don't cancel out the logs here. Even if you got the right answer, it's not really the right thing you should be doing there. We end up with the linear equation minus 2 minus 5x equals 2x plus 16. I'll add 5x to both sides. So it puts the variable on the right-hand side. To get the constant on the left-hand side, I'll subtract 16. So I get negative 14 equals 7x, or negative 2 for x. We can check negative 2. In fact, we should check negative 2. It's not wrong that it's a negative. We just can't take the log of a negative number. So when I check it, I want to go back to the original equation. So it's the log of 2 minus 5 times negative 2 over 2 times negative 2 plus 8, which is going to be the log in the numerator of 12. So the log of 12 over 12. In fact, log of 12 over 12 is 1. Now you have two choices. Either you can think about it or you can take out your calculator. Either way, what's the log of 1? You're asking yourself, what power of 10 gives me 1? It's the 0 power. So it checks. So nice. So I think we've kind of exhausted method 1, where we have the log of something equals the log of something else. And this problem actually lends itself to another method. And it's something that you're going to have to do if you can't write your problem or work your problem to a point where you have the log of something equals the log of something else. Method 2. And you've actually already used method 2. Let's go over method 2. Method 2 is simply to rewrite the equation using exponents. And we've done that. If you have log base a of x equals y, then that turns into a to the y power equals x. We can actually do that for problem 72. And let's see what happens. So I'll go back to this log of 2 minus 5x over 2x plus 16 equals 0. And because it's not actually written there, let me put it in for us. What base of log is understood to be here? 10. So if I rewrite this now using exponentials, then it would be 10 to that power equals this. It's always that kind of little whirlwind pattern like a tornado on a weather map. It's going to be 10 to the 0 power equals 2 minus 5x over 2x plus 16. Can anyone tell me what 10 to the 0 power is going to equal? 1. So I'll rewrite that as a 1 equals 2 minus 5x over 2x plus 16. You've got something that you guys all love in your math problems, and it is fractions. Yay. So I'll tell you what, let's get rid of the fractions. How could I get rid of the fractions? Good. Multiply both sides by 2x plus 16. Basically, you're multiplying both sides by the lowest common denominator. And what's nice is that lowest common denominator is going to cancel on the right-hand side. You're left with 2x plus 16 equals 2 minus 5x. And from here, we've solved this one. we already know based on our work up above that x is equal to -2. So I'm not going to finish that part. The part you should see, though, is how we rewrote this. Now, in this one and ones like it, you didn't have to use this second method. You could have used the first method, and there's nothing wrong with that. I'm not going to tell you you have to use this one or you have to use that one. But sometimes you don't have any choice. So let's do a few problems where we don't really have much choice in what approach we take. Before I move on, is there any little nuance about this that maybe I went over too fast? No. Okay. Let's try problem 64. Kind of a little warm-up problem here for us. ln of x equals 5. A little bit tricky in as much as they don't really give us a base there. At least it's not written. Thank you, ladies. It's log base e of x equals 5. And maybe having it written there explicitly. And I'm a big fan of replacing log of or ln of x by log base e because it gives you something that you can see there. It's a little bit easier to rewrite this as an equivalent equation using exponents. So, who haven't I picked on yet today? Cody. Have I picked on Julie yet today? No, I haven't. He threw you under the bus. All right. So, Julie, can you rewrite this using exponents for us, please? All right, thank you. E to the 5th power equals x. Oh, I'm sorry. Are we done with this problem then? Yes.
That was easy.
Cool. All right, so that's it. All right, we just rewrote it using exponents. Now, sometimes it's going to be a little bit more challenging than that, but I'll specify if I want a decimal or not. So basically, you can leave it like that unless I specifically ask for a decimal. So appreciate the question there. Okay, so what about a problem like number 44? Log base 4 of 2x minus 1 equals 3. So, again, you want to rewrite this using exponents. Is there anyone else I haven't called on yet today? Anyone? Any volunteers? Oh, yeah, thank you. I heard that. Fortunately, the mic is not that sensitive. That day I did the recording for you guys, everything with it. There was vacuuming in the hallway. There was somebody with the subwoofers cranked up to 10 out in the parking lot. Trains were going by. I was going nuts. All right, so go ahead. Write it with exponents. Perfect. 4 to the 3rd equals 2x minus 1. So 64 equals 2x minus 1. 65 equals 2x. Or 65 over 2 equals x. Thank you. Good job. And that's it. Yay. Nice. Now, how come I couldn't use our other method? Oh, Cody? Yeah. No. I mean, I prefer the fractions, but if you gave me 32.5, that's fine. There's nothing wrong with that at all. How come I couldn't use the first method in this case? The first approach we did, where we had the log of something equals the log of something else. Yeah, I don't have the log of 3 on the right-hand side. It's just the 3. If I had a log of 3 on the right-hand side, then I'd be in business. But in absence of the log term there, you can't just, put the log in there and say, oh boy, there we go. Now that's an easy problem. All right, it'd be nice, but you can't do that. That's why you need kind of another method here. And we've got that. So if not everything is part of a log term, then you're probably going to be stuck using method 2, as I'm calling it. And by the way, I'm not going to ask you, method 2, method 1. You're just going to have to know how to solve these things. Let's try another one. Problem number, we'll keep it easy here. Build our way up. Problem number 48. Log of 1/5 x equals -3. See what you can do on this one. Start by reminding yourself what log we're dealing with, what base. Brandon, can you rewrite this using exponents for me?
10 to the -3 equals 1/5.
All right, perfect. So 10 to the -3 equals 1/5 x. What's a different way I could write 10 to the -3? 1 over 10 cubed, or better yet, 1 over 1,000 equals 1/5 times x. How do I solve for x in this case? Divide by 1/5. Dividing by a fraction is the same thing as multiplying by the reciprocal, so I'm just going to multiply both sides by 5. So I get 5 over 1,000, which is 1 over 200, which is x. Yay. Nice. Not too bad. Not too bad. Let's try a couple more. Are you okay with 48? Let's try problem number 82. 82 is going to be kind of a big step up. So as I'm going through it, if you have some questions, please let me know. Two times the log of 3, 2 times log base 3 of x, minus the log base 3 of x minus 4 equals 2 plus the log base 3 of 2. Wow, what a mess. There's one thing I want to point out about this particular problem that kind of gives you a little guidance as to what way you're going to have to do it, method 1 or method 2. And the thing I want to point out is that that 2 is all by itself. It's not part of a logarithm. You're not going to be able to write this as the log of something equals the log of something else. So you kind of have to rewrite this. Now, in order to rewrite this, what I'm going to do is I'm going to put all the log terms on one side. So 2 log base 3 of x minus log base 3 of x minus 4 minus log of 2 equals 2. All right, well, now I need to write this using one logarithmic term. So let's do this. Let's use our properties of logs in kind of an opposite direction. I want all these coefficients to equal 1. So this is practice with our properties of logs from the other day. This becomes log base 3 of x squared plus log base 3 of x minus 4 to the negative first plus log of 2 to the negative first. And what I'm working my way down to is I want one logarithm on the left-hand side. I want to write that with one logarithmic term. I'm almost there. Do you remember what happens with the sum of the logs? How can I rewrite that one? Good. They multiply. Remember the log cabin thing, right? All right, it's that example that we can use here. This is exactly the log cabin thing. So this becomes a log base 3 of x squared times x minus 4 to the negative first times 2 to the negative first. Log of all of that equals 2. What can I help with? There's something that didn't look right to somebody.
You're looking at me. You just put the log of 3 in the second line.
Oh. Thank you. Log 3 in both of these. Okay. Let's clean this up just a little bit before we rewrite it. Remember what we did the other day? We got rid of these negative exponents. So the last step here, this is log base 3 of x squared over a 2 and x minus 4. Whew. Are you okay with that last step there? I'm going to distribute that 2 in the denominator. Wow, I've come a long ways to do yet even more work. So I'll pause here, let you get out the oxygen bottle, take a good hit out of it, and get ready to charge on. Okay, so try and rewrite this now using exponents. Much the same way we've done with a couple of the previous problems. The base to the power on the right-hand side equals our argument. So see if you can't rewrite that. Okay. What's this going to look like? Lily, when I rewrite it using exponents, what's it going to look like, please?
3 squared equals x squared over 2x minus 8.
Perfect. 3 squared equals x squared over 2x minus 8. Of course, 3 squared is 9. All right. Yes. So we've got an equation that involves a fraction here. What we'll do is we'll get rid of that fraction, multiply by 2x minus 8 on both sides. So on the right-hand side, we get some nice simplification. On the left-hand side, we're going to have to do some multiplication, but those cancel. So I get x squared equals 18x minus 72. Wow. Hey, the good news is we're halfway done. All right, I'm kidding. We're a little bit more than halfway done. But this is a quadratic equation. How do you solve quadratic equations? Yeah, let's get 0 on one side. Now, since x squared is on the right-hand side and it's already positive, I'm going to move these two terms to the right-hand side. So if I do that, sweet, let me come back to you. If I write 0 on one side and the left-hand side, what's the equation then? Nice. X squared minus 18x plus 72. Should I pull out the quadratic formula for that one? No. I shouldn't. I mean, you could. It's like burning down a house to roast a pig, but no, let's try something else. What else can we try there? Factor it, sure. Thanks, Norman. So I need two numbers that multiply to 72 and add to negative 18. So I'm guessing that both of them will be negative because a negative times a negative will give me a positive. Two numbers that multiply to 72 and add to 18. Good. 12 and 6. So I get two possible solutions, x equals 12 and x equals 6. Now you do have to check these, but let me give you kind of like the minimum that you need to do. I mean, it'd be nice to check them completely, but in a problem like this, it'd be kind of difficult. The minimum you need to do is make sure that when you put these in, that you're not going to end up taking the log of a negative number. Well, if I put in a 12 or a 6 here, that's not going to give me the log of a negative number. 6 minus 4 or 12 minus 4, those are both positive, so they're looking okay. And especially if this factored so nice and neatly, we can feel pretty confident that we did this one right. All right, quite a long problem on that one. Did a lot of steps. Is there something that I glossed over a little too quickly that you'd like to review some? Nothing there. Okay. Let's do a few more here. In fact, let's move towards, okay, I'm going to give you kind of a little bit of a warm-up, and then we're going to work on a few of the problems that deal with radioactive decay. Maybe some interest or bacterial growth or something too. Carbon-14 dating. So this isn't, like the matchmaker.com dating. It's trying to figure out how old something is. And we can do that because a lot of things, a lot of elements follow an exponential growth or decay kind of pattern. Carbon-14 is one of them. Now, to kind of give you a little feel for carbon-14 dating, let me give you an equation that governs carbon-14 decay. So it's a radioactive decay where carbon-14 changes into, I think, carbon-12 and maybe some nitrogen someplace, I'm not sure. SU12T. So what's this equation represent? Well, A sub 0 is the initial amount. A is the final amount, so how much you start with and how much you end with. And t is time. And in this case, in years. So what I want you to play with is how much of an initial 100 grams is left. Let's just say 100 grams of C14 is left after 5,730 years. So basically what I want you to do is I want you to put in 5,730 for t and 100 for a sub 0. And calculate that number. That number is going to be your final amount. And in this problem, I'm calling it A. But take out your calculators. And what I want you to do in particular is I want you to round your answer to the nearest whole number. Because there's a special relationship here that I want you to see. So take out your calculators, plug that in. Now where do you find e to some power? Where's that button? Yeah, it's right above the ln. So you have to hit the second key and then the ln key in order to get e to some power. So second ln. Now if you got a calculator that's old school, it would give you a little up arrow thing and then a left parenthesis. Type in a negative off the bottom of your calculator. Do not use the subtraction key to type in negative exponent like that. Negative 0.000121 times 5,730. Y'all able to get this number? What's that round to? The nearest whole number, what's that rounding to? 50. Now how does 50 compare to what you started with? It's half. So for that reason, they declare that 5,730 years is the half-life for carbon-14. It takes that long for that substance to decay down to about half of what it started out with. So in another 5,730 years, you'd have 25 grams left because this half will decay down to half again. And after another 5,730 years, you have about 12 and a half. It's a statistical average. It's not mathematically rigorously precise, but it's an average, and it's pretty good. They can date things within 2 or 3% of their actual age. So you okay with that part? I'm not trying to make you an expert on carbon dating. Far from it. What I want to get at is the math here. So let's practice a couple problems with the math. Now, I'll give you a little help here with problem number 108. And actually, the help is already given for the most part because we've got this equation. The way I read the book, you'd actually have to figure out that equation for yourself. But I'm going to be a little bit kinder and gentler to you. So it says only 10% of the carbon-14 in the small wooden bowl remains. How old is the bowl? Okay. Now, it doesn't seem like they're giving us a whole lot here, does it? It's the first part that's a little bit challenging. It says only 10% of the carbon-14 in a small wooden bowl remains. 10% of what? Well, it's 10% of what you started out with. That A sub 0 here. So there's three kind of things that we can plug in here. A sub 0, and T. T, the age, is what we're trying to find out. A sub 0 is how much carbon-14 we started out with. We don't know that. But here's what we do know. We ended up with 10% of what we started out with. %10 of what we started out with. We started out with A sub 0, so it's 10% of A sub 0, or better yet, this right here. And that's kind of challenging, is to come up with that expression. For that, that's how much we have left. So what I'm going to do is I'm going to take and plug that into this equation. I have 10% A sub 0 equals A sub 0 e to this exponent. And I've done a lot of talking and some substituting, and it doesn't really look like I've gotten anywhere. But that's not quite true. What I'm going to do is I'm going to divide both sides by A sub 0. Does it really matter how much I started out with? Not really, because it cancels on both sides. What I'm left with is this. 0.10 equals e to the negative 0.000121 t. This is where I want you to be able to solve things. This is an equation that you should be able to dig your teeth into. What kind of an equation is it? I'll give you a hint. We've used the name today. Thank you. It's an exponential equation. What do we do to solve our exponential equations? Wow. It's been less than half an hour, or maybe about 40 minutes. Go back and look. What do we do to solve your exponential equations? Take the log of each side. In fact, because of this one, the way it's set up, how about if I take a special base log? Let's take the ln on both sides. Well, tell you what, I'm going to split the difference. I'm going to write ln on the left-hand side. I'm going to write log base e on the right-hand side, because I want to remind you that there's going to be some nice simplification on the right-hand side. I just as easily could have written log base e. Maybe I should have. Log base e. Log base e is, of course, ln of 0.10. The right-hand side simplifies as well. What do I get on the right-hand side? You get some really nice simplification there. Well, tell you what, let's do it kind of in pieces. Let's take the exponent out in front. I get minus 0.000121 t times the log base e of e. Can anyone simplify the log base e of e for me? 1. Thank you.
So what I get is ln of 0.10 is that coefficient times t. Almost done here. What's the last step to solve here? Divide. You're going to take the ln of 0.10 divided by negative 0.000121,
And that should be your t.
So let's do that. Let's get a numerical value for that. So ln of 0.1 divided by negative 0.000121. You should get about 19,000 years. Don't forget to include that negative when you divide.
Yeah, please. They just rounded it off to the nearest year. I mean, this method is not that accurate that you can say 19,029.628 years. I mean, mathematically, that's what you're going to get, but I think this is probably good to within a couple hundred years at that point. It really depends on where you're at in terms of how old something is. This method is a little bit tougher, a little bit sketchier when you're dealing with something really, really old. Because basically what happens is that there's a lot less carbon-14 at that point. If you're off by 1 or 2 when you're counting to 1,000, that's not such a big deal. If you're off by 1 or 2 when you count to 10, that is a big deal. And that's what's happening when you're dealing with something really, really old. After some point, they start using different methods, like potassium argon dating, that kind of thing. So, yeah, there's limits to how far you can get with carbon-14 dating. Let's do one more like that. Kind of similar, a little bit differently. Bacterial growth. So it's problem number 114. Still not there. Oops, other way. Okay, so a bacterial culture grows according to this function. Now that p sub 0 is going to be, again, your beginning amount. T is going to be time. And P of t is kind of your final amount. So let me write those things down. It takes 5 days for a culture to triple in size. How long will it take to double in size? So again, that's going to lead to an exponential equation. Let me write a few things down here for you. So P of t equals P sub 0 e to the t. Let's try and focus that. There we go. It takes 5 days for the culture to triple in size. You know what? I didn't copy this down quite right, did I? They have an A here. I was thinking this was going to be an E. So they're not telling us A. Let me rewrite that. P of t equals P sub 0 A to the t. But what they do tell us is that after 5 days, t equals 5, the final amount is triple the beginning amount. So t is 5,
P sub 0 just stays, but the final amount is going to be 3 times the initial amount. So let's put that in. 3 times P sub 0 equals P sub 0 a to the 5th. Okay. Notice that I got P sub 0 on both sides. Divide both sides by that P sub 0. And now I want to solve for A. Actually, you don't need to use logs at all in this case. Why not? This isn't an exponential equation, is it? Why is this not an exponential equation? Because the variable is the base, it's not the exponent. So I can solve this one by raising both sides to the 1/5 power. So I get the 5th root of 3 equals, excuse me, this should be the 5th root. 5th root of 3 equals A. So let me rewrite my model then. It's P of t equals P sub 0 times A to the 3 to the 1/5 t. That's my model. I'm just using 3 to the 1/5 as opposed to A. This is a lot harder than what I would put on the test. Let me show you what I would put on a test. What's a fair game problem for the test? And that is, they want to know when this population is going to double. That's going to double when you end up with 2 P sub 0. T times 1/5, I'll write that as T over 5. So where this becomes an equation that I would have you work on or could have you work on is right here. 2 equals t to the 3/5 power. Okay, that one's doable. This is an exponential equation, unlike the previous part of this. So this is where you should make sure that you can solve things. To solve exponential equations, we can take the log on both sides. That t to the 5/2 comes out in front. Log of 2 equals t over 5 log of 3. And I want to solve for t. So to solve for t, I'll multiply by 5 on both sides. That cancels out that. So 5 log of 2. And then finish by dividing. So divide both sides by log of 3. 5 log of 2 divided by log of 3 equals t. So if you calculate it on your calculator, you get about 3.15 days. So a little bit more than 3 days for that population to double. Okay.